In the previous video, I talked about realRAM. So it's a machine that has real registers that can store real numbers up to infinite precision, and they can do basic operations such as the Kate root in constant time, again up to infinite precision. Why do we need this machine? It is not actually clear that we need this machine, but it turns out that lots of algorithms are very easy to analyze on this machine. And if we don't have this model of computation, then we run into some kind of annoying theoretical problems. And the most famous one is this one. So let's say you have 2 points, A and B, and you have 2 paths. Let's say, just think of Google Maps. You can go this way on these roads to get to B, or you can go onto the blue one. And you know everything about these. So you know the coordinates of A and B, and let's say they are integers. You know the coordinates of every vertex of the red path and every vertex of the blue path. And now what you want to do is to figure out which path is shorter. So obviously you could know the length of every line segment is a formula that has a square root, right? Because the length of a line segment is a square root of differences between x coordinate squared and the y coordinate squared. Okay, so it's a very simple formula, but it has a square root in it. If the coordinates are integer, that boils down to a square root of an integer. Another question is, let's say if the red path has n line segments and the blue path has n line segments, is whether or not the sum of n square root is smaller than sum of some other n square roots, and all these numbers are integers. If we don't have this machine, so let's say if I cross out this machine, and let's say we're working on this machine over here, where I have registers of W bits and basic arithmetic operation take constant time, I could represent this problem because the input to this problem is just a bunch of integers, right? So I have n integers xi and I have n integers yi. So this problem can be represented in this model. And now this machine only needs to decide whether this summation is smaller than this summation or not. The problem is that this is not known to be done in polynomial time. It might be possible to do it in polynomial time, but we haven't figured out how to do it. The basic problem is basically this one, that you have a bunch of integers and you want to compare the sum of their square roots. So for example, in this problem, the issue is that the sum of the square roots could be very, very close to each other. So it's not clear how much into the precision we need to compute the square root. So for example, let's say you have 3 numbers, 3 line segments for the red and 3 line segments for the blue. Right? So you're comparing square root of 5 plus the square root of 6 plus the square root of 18 to square root of 4 plus the square root of 12 plus the square root of 12. One way to do this comparison is to compute each one of these square roots up to a certain precision, then add them up and see whether the result is positive or negative. Okay? And in this particular example, you have numbers that are very small, up to 20, but you need to go, I don't know how many digits of precision into the calculation of your square root until you figure out that this number is actually larger than that summation. In general, it is not known how deep we have to go. Obviously, we cannot go, obviously if the 2 numbers are equal, then at some point we have to break away and say that they are equal. Let's say if you calculate these 2 numbers, these summations up to 1,000,000 digits, and if they're still equal, can we say for sure that they're equal, or should we go a bit more? That's not clear. So that's basically is the problem. It's an old problem, and there's a quotation by David Epstein, one of the major researchers in computational geometry, that a major bottleneck in proving completeness for geometric problems is a mismatch between the real number and Turing machine models of computation. One is good for geometric algorithms but bad for reductions, and the other vice versa. Specifically, it's not known for Turing machines how quickly to compare the sum of distances with an integer or similar sums to so even easy algorithms such as minimum spanning tree are not known to be in NP. Okay, so this is a very theoretical problem. Obviously, from a practical point of view, if you have such an instance where the 2 paths are equal up to 100 digits of precision, then you really don't care which one is shorter. But when it comes to theory, that's a major problem. So therefore, theoreticians have invented a completely nonsensical machine called realRAM. And during the course, we're going to analyze all of our algorithms using this realRAM machine. And obviously, when you implement algorithms, you will see that how painful it is to deal with a machine that looks more like this one. Okay? But as you can see, there is already a very big disconnect between theory and practice when it comes to computational geometry. We invented a completely unrealistic machine, and we are now designing algorithms for this machine. So obviously there will be instances where this machine does not match practice, or the algorithms that run on this machine will not match practice.